Hello everyone, this is Miss C. I'm going to talk today about the chemistry chapter in the Campbell AP Biology textbook, and hopefully it will help rekindle some memories of chemistry, but also get you the basics you need for this class. So chemistry. So some of the biggest things you'll need to know and make sure you understand about chemistry is the whole idea of what is mass, what is matter. So everything's made up of atoms or elements, okay? So when we have elements, those are going to be the substances that cannot be broken down any further. Okay, so those are going to be things like your oxygen, your hydrogen, your nitrogen, okay? When you talk about a compound is going to be those things like sodium chloride in this example here. So here's the sodium, here is the chloride, and now we have table salt, sodium chloride. Okay, so these are two or more elements joined together. Okay. Trace elements are really important when it comes to talking about biology because our major elements that we are going to find are these right here. So we've got oxygen, carbon, hydrogen, and nitrogen. Okay, so sometimes you'll see it like this or made into little words, little acronyms that you can use, okay? Then you'll have these other that are called trace elements. And trace elements are just basically elements that are found in minute quantities, but they are very important and needed. For instance, iodine is a trace element. It's not on this chart, but it is a trace element. And it's important because if you don't get enough iodine, you get what's called goiter, where you have a big golf ball size to basketball size growth on your neck. Okay. All right, so let's talk about the properties of elements and atomic structure. Again, this should be review, so hopefully you'll recognize these things. All right, so you have your electrons, and well, first let's look at the atom itself. So these are two different diagrams you can look at. This one more accurately shows what the atoms look like. So you have your nucleus in the center with your protons and neutrons, and then you have your cloud of negative charge. In this case, there's two electrons which have created this negative charge on the outside. Here you can see those electrons a little bit more clearly. They're constantly moving around and around and around. And so this one shows you kind of where they're going. So a lot of scribbling, but hopefully you get the idea that electrons don't just stay still. They are constantly moving on the outer parts of the nucleus. Okay, so the structure of an atom we just talked about. You have your neutrons, which are in the center. You have your protons, which are also in the center of the nucleus, and then your electrons. Okay. So when you're determining your atomic number, it's always going to be the number of protons. Okay, so if you're looking at, let's say, the element helium, and you see a written subscript like this, this signifies the number of protons. Okay, the atomic mass, on the other hand, comes from the nucleus. So the mass comes from the nucleus. And you are going to see electrons not contributing a whole lot of mass, very little mass, okay? So a big part of your atomic mass comes from the neutrons and the protons, okay? So that would be expressed in Daltons, and that's that number that typically has the decimal. So for sodium, the atomic mass is 22.9. 898. Okay. Sometimes though they'll abbreviate it to say it's 23 Daltons. Okay. The mass number is that number that's going to look at the number of protons and the number, of neutrons. And that's going to give us our our mass number. So again, we go back to helium. We see that elements, the symbol, we have the number of protons, and then the number up here is the number of protons plus the number of neutrons. Okay, so this would be what you typically see when you're looking at elements and showing what their mass is and their atomic number and their mass number. Okay, isotopes are another interesting part of chemistry. We do talk a lot about it in biology because they do have many biological purposes. So an isotope basically is just an element that has same number of protons but not neutrons. So they differ in the number of neutrons they have. So here we have protium, which is a isotope of hydrogen. We've got 1 proton. Here we've got 1 proton, still again staying the same, but now we've added a neutron. And so this is deuterium. Okay, and then same thing, 1 proton still, but now we have 2 neutrons, and this is tritium. So again, these are isotopes of hydrogen, so we're still dealing with the same atom or the same element, but we are now changing its number of neutrons, which is beginning to basically make it a little unstable. Okay, so with that said, some are radioactive. Okay, so some biological practices or applications of isotopes, radioactive ones particularly, is in dating fossils, so carbon dating, things like that. Okay, tracing atoms and metabolic processes, so tracing atoms in metabolic processes. And then more importantly, what we probably are more familiar with is diagnosing disorders or diseases, so the diagnosing medical disorders. Okay, so just briefly, I'm not going to get too crazy in the energy levels of electrons because then we have to start talking about orbitals, and I'm not about to do that, trust me. When we talk about the energy level of electrons, we're talking about how electrons, as they go down their energy level, okay, they start to gain more energy. Okay, so a good picture to look at is this one, where you see as we move up in levels, so this is the first, second, third, as we move up in level, we have energy absorbed, meaning energy is being stored. When we go down in the opposite direction, energy is lost, which means energy was released. So stored, released. Okay. All right, let's talk about chemical bonds. So there are several types of bonds that we explore, especially in chemistry. You're going to come over a lot of them. The ones that we're going to concern ourselves with are the covalent bonds and the ionic bonds. And within those, there are some that we need to pay close attention to. Okay, so just to recap, single bonds are when you have sharing of electrons. So, okay, double bonds are when you have sharing of 2, and these are, valence electrons. Okay, so sharing of 2 valence electrons, and then obviously here we're going to be sharing 3 valence electrons. So I like to remember covalent, they're coexisting, they're cohabitating, so they're sharing. It's kind of the only way I really remember it. So we have polar bonds, which are going to share basically these electrons equally. Okay, the charges are going to be equal. They're going to be pretty much kind of a give and take, so they're not going to be super negative or super positive. They're going to share equally, or unequally rather. Then you have your nonpolar, which are going to share, sorry, let's change this to unequally. Your electrons shared equally. Okay, so I apologize. That was supposed to be unequally over for polar. Nonpolar is they're shared equally. Okay. So an example that you guys are familiar with is water, but we're going to first talk about these covalent bonds that happen between hydrogen, so they're sharing, between oxygen, so this should be O2 right here, so they're sharing these equally, so we've got a double bond here, a single bond there. Okay, water is a superpolar molecule. One of its properties is that it's polar. What makes it polar? Well, oxygen is slightly more electronegative than hydrogen. So the electrons are actually going to be pulled more towards oxygen, and so that's going to make it kind of a stronger bond. It also gives a partial negative charge because those electrons are pulling towards oxygen more than they're pulling towards hydrogen. Okay, now we talk about ionic bonds. Ionic bonds are going to be those bonds that are going to basically strip each atom's electrons from each other, depending on what atoms they are. So, for instance, in sodium chloride, the electron for sodium gets stripped from sodium and gets added onto chloride. So now chloride has an extra electron, and now sodium is missing one, hence why we have these now charges on both. So now sodium and chloride have become ions. Okay, a cation, all it is a positively charged atom. This is negatively charged. Okay, and at the end of the day, the bond between an ion and a cation becomes an ionic bond. So this is bond between anion and cation. Okay, all right. So now let's talk about weak chemical bonds. So there's two really important ones we talk about. One of them being the hydrogen bond, which happens between two molecules of water. Okay, a hydrogen bond basically is a non-covalent bond, so it's non-covalent, and it's going to be between a hydrogen and an electronegative molecule, or sorry, atom. An example would be oxygen, which we just talked about with water being polar, and nitrogen. Okay, your van der Waals interactions are going to be basically when two atoms are so close together that they are going to form a pretty strong bond. Okay, those fleeting charge differences is what ends up attracting them to each other, and then several of them is really strong. So animals like this gecko, on the pads of its feet, it's made up so that they have van der Waals interactions between their feet and whatever they're climbing on. So that keeps it very strong. Think about this gecko trying to crawl on the ceiling. It's going to need a lot of strength and its bonds between its feet and the ceiling to stay on the wall or on the ceiling and not fall. Okay, what's the biological importance of weak bonds? Well, basically, they're easily broken. Okay, hence why they're called weak bonds. However, when they are formed, they help stabilize molecules, especially our biological molecules that we care about the most. An example being DNA. Okay, they are held together, the two sides are held together by hydrogen bonds. Those bonds have to be strong, otherwise DNA will quickly unravel. However, they have to be weak enough that they can be broken when DNA replication occurs or protein synthesis when RNA has to make a copy. Okay, molecular shape and structure, super important. Okay, we talked earlier about function and form in biological systems. Same works for molecular shapes. They're all going to have a certain structure, and based on their structure have a certain function that helps. So remember, with the molecular shape, most are linear. Okay, there are those that have the orbitals, which create a 3D shape. Okay, the reasons for these shapes is that shape helps biomolecules recognize and respond. Okay, so here's an example. So this is natural endorphin. So we release endorphins, and those are the signals that make us happy, that kind of calm us down, make us feel good. Well, morphine has a very similar chemical structure on a part of it, as you can see here. Okay, so what happens is that these endorphins and morphine cannot be distinguished as different from the receptors in the brain. So the brain receptors, if they recognize this general shape, they're going to accept it. So this is the reason why morphine is a really addictive drug, because it makes us happy. It's basically mimicking endorphins. And who wouldn't, in terms of the brain, want as many endorphins as you can get? Okay, so these opiates, so that's going to include heroin. Those are the reasons why they become so addictive, because of the structure it shares with a natural endorphin. Okay, and then quickly to end it out, we've got our chemical reactions. So just again, remembering, when you have chemical reactions, you've got your reactants. So here we've got 2H2, we've got O2. A chemical reaction occurs, and then now we get our products, which is 2H2O. Okay, you don't have to necessarily remember how to balance. You know you're going to make sure to do that. In this case, we had 2H2 and an O2, so we had to make two water molecules. But we're not going to get more complicated than that. So please go ahead and look over the video again if you need to. Read your textbook, and hope that this was helpful for you.